Dear listeners, welcome to today's webinar. The topic of the webinar is Neurodegenerative Diseases, studying protein aggregation using NanoTemper instruments. I'm your moderator for today. My name is Aiga, and I'm a student at the Technical University of Munich. Here with me is the speaker of today's webinar, Dr. Andreas Lange. He obtained his doctor's degree from the Technical University of Munich in the field of biophysics. He is currently working as a senior application specialist at NanoTemper Technologies.
Hi Iga, thanks for the introduction and great to be here. So before I start and tell you more about NanoTemper solutions in the field of neurodegenerative diseases, I would like to ask you a simple question. What age would you like to live to?
Good question. Well, I would say around 80, 85.
Excellent, great answer. Yeah, in general, when you ask people how long they would like to live, most of them will tell you an age between 79 and 100 years. And that's not so unrealistic. If you have a look at the average life expectancy, we can see a clear trend in the world. So, for example, children born in the 1960s have an average life expectancy of around 70 years, while children that are born today will live about 10 years longer. So life expectancy is constantly increasing, and that's a fantastic thing because it means that when we're old, we will have more time to travel the world, and hopefully we'll soon have again flights to bring us there. We have more time to spend with our families and our friends. We'll also have more time to do great science, and maybe that's more important now than ever. But unfortunately, it also means that we will have more time to suffer from neurodegenerative diseases. The reason is that aging is the primary risk factor for most neurodegenerative disorders. If we, for example, look at Alzheimer's disease, which is the most common neurodegenerative disorder, if you're younger than 65, then the chance that you will have this disease is only 3%. However, if you're older than 85, then this chance increases to about 36%. So with all of us getting older, it's very likely that at some point in our lives, either we will have this disease or we will have at least someone in our family who has it. In fact, in the United States, every 65 seconds, a person gets Alzheimer's disease. And as we get better at curing other diseases like heart diseases or cancer, this implicates also that more people will eventually die from neurodegenerative disorders. And you can only imagine what impact this will have on our families, our society, and our healthcare systems. So there's a big incentive for companies to invest money into searching for new treatments and cures. And this is what's happening. So since the year 2000, pharma companies have invested more than 600 billion US dollars in the search for new treatments and cures. However, for every successful treatment that has been found, there have been 37 failures. So there's an incredibly low success rate. In addition, all the treatments that we have found until now are only symptomatic. So we don't have a cure for these diseases. We can only treat the symptoms. The reason is that there's still a huge knowledge gap on what causes these diseases and, for example, whether these molecular characteristics that we are seeing in the brains of patients, if they are causes, effects, or maybe simply signs of progression. And this makes it really challenging to identify and select new targets for therapies. There is one common characteristic of all neurodegenerative diseases, and that is protein aggregation. So depending on what type of disease it is, different parts of the brain are affected, and therefore also different proteins are forming these protein aggregates. For example, in Alzheimer's disease, it's mainly the tau protein and the amyloid beta that form the A-beta plaques and the neurofibrillary tangles of tau. In Parkinson's disease, it's, for example, alpha-synuclein. And as these aggregates form and get more and more in their numbers, this can lead to the degeneration and death of neurons. And that's then what causes these classical symptoms that we are familiar with from patients, for example, the impaired body movement or the loss of memory. What makes research in particular difficult here is that most of these proteins that are involved in the neurodegenerative disorders and in protein aggregation, they belong to a class of proteins which is called intrinsically disordered proteins. And these are proteins that, as the name says, don't have a proper folding, for example, like a globular enzyme, but they are intrinsically unfolded. Of course, there are common methods that are used to study these proteins. There's, for example, ITC and SPR, which are used for ligand binding measurements. There's also the famous theoflavine T binding assay, which involves a dye that binds to beta sheet-rich structures and can visualize aggregates. But all these methods have their pros and cons. For example, ITC can be very time-consuming, and you need large amounts of sample that you not always have available. Also, it can be difficult to differentiate between binding and aggregation if both happen at the same time. THT assays, on the other hand, are very fast, but the dye only specifically binds to beta sheet structures. This means that you can visualize larger aggregates and fibrils, but you cannot see the smaller oligomeric intermediates. And that's a problem because recent studies have shown that it's not the large aggregates that are dangerous, but it's rather the small oligomers, because they are still mobile and they can even travel between neurons. So healthy neurons can be infected, a bit like through a virus. And lastly, SPR is a method which needs a molecular weight change to detect binding. And that's not always easy to have, because if you have a large aggregate binding to a very small aggregation inhibitor, for example, which can be a small molecule, then the change in molecular weight is not very big. Also, immobilization can change the conformational equilibrium of the protein. So it might adopt a totally different conformation on the surface than that it has in the solution. And this is where the MST method used in our monolith instrument addresses the gaps. For example, MST is very fast and requires only a tiny amount of sample. Also, you get a direct feedback on aggregation in every measurement. Compared to THT assays, MST can differentiate between monomers, dimers and oligomers, and larger fibrils. And finally, MST is independent on molecular weight changes, and it's an in-solution measurement, so no proteins need to be immobilized. To demonstrate you the advantages of the MST technology, I would like to show you some recent data on tau protein that we have obtained in our labs in Munich using the monolith instrument. Tau is an intrinsically disordered protein that in healthy neurons stabilizes the microtubules. In Alzheimer's disease, however, these tau proteins can get hyperphosphorylated and then fall off and form these soluble tau oligomers, which can turn into neurofibrillary tangles and cause cell death. There also have been a number of publications over the last 10 years that show that zinc ions as well seem to be involved in this tau aggregation. Importantly, it could be shown that low micromolar concentrations of zinc can accelerate tau fibrillation. I've copied here a very nice scheme on the left side, which shows a bit how this interaction is supposed to happen. So we see here tau monomers, which can bind to zinc at low concentrations, forming these tau-zinc complexes. But then at higher concentrations of zinc, there are additional binding sites on this long, intrinsically disordered protein that can cause the tau fibrillation. So you can imagine it's very difficult to measure this interaction because zinc ions have a very low molecular weight. And then we have this combination of binding, we have several binding sites, and we have aggregation happening at the same time. Therefore, we were very curious to see if we can get some meaningful data on this interaction using our MST technology. We did a very simple experiment. We took some monomeric full-length tau protein and labeled it using our second generation NHS dye. Then we mixed this labeled protein with a dilution series of zinc. And this is the dose response that we got. So you can see until a concentration of around 5 micromolar, there's no interaction between tau and zinc. Then at around 10 micromolar, we see a steep increase, followed by a second transition at around 50 micromolar. So MST shows that there must be at least two types of binding sites for zinc, a higher affinity one and a lower affinity one. And this fits very nicely to this hypothetical scheme that I've showed you in the slide before. We also could show that this interaction is completely reversible by adding EDTA. So it's really a specific interaction between zinc and tau. What came as a big surprise to us was to see how steep this first transition here is when the first zinc ion binds to tau at around 10 micromolar. So we repeated the experiment using another dilution series with a much smaller spacing in between concentrations in order to get more data points in this transition region. And this is a curve that we obtained. You can see it's still so steep that you cannot fit this anymore using the classical KD model. You have to apply a model called the Hill model, which is usually used in cooperative binding. And when you do this, you get a Hill coefficient of about 11. That's a really, really high value. So zinc seems to bind tau with an apparently high cooperativity. And that was very surprising to us because, to our best knowledge, this hasn't been reported yet in literature. But there are even more secrets hidden in the data. For example, before I told you that MST can also give you feedback on protein aggregation. This works by looking at the MST raw data or the MST traces, as you can see here. If these traces become bumpy and wavy, this usually means that we have some sort of protein aggregates in our sample. If we look at the tau-zinc interaction and we do an MST measurement directly after mixing, we can see that the MST traces all look very nice and clean, and there are no signs of such aggregation. This means that zinc binds to tau immediately after mixing, and the tau stays in its monomeric form. However, if we wait for a couple of minutes, for example 20 minutes here, we can see that at the highest concentrations of zinc, the curves start to go up and down and become bumpy. This means that here, the tau starts to form aggregates. If we even wait a bit longer, for example 40 minutes, then even at some lower concentrations of zinc, we also observe this change. So MST allows us to monitor the zinc-induced tau aggregation over time, and the observed concentration and time dependence is actually in great agreement with published TU-Flavin binding assays. Moreover, if we go back to the dose-response curve here, we can see that it's only these concentrations depicted here on the right that cause aggregation. So in order for tau to fibrilize, we need the second binding event of zinc. Okay, I hope I could show you a bit how protein aggregation in neurodegenerative diseases can be studied using our instruments. Apart from the studies of the physical parameters that I've just shown you, you can find many publications out there where scientists, for example, have used our instruments to look into the basic molecular mechanisms of protein aggregation. Also, currently, there are a lot of people interested in finding new therapeutic agents, such as aggregation inhibitors, that would be molecules like small molecules or antibodies that can prevent aggregation from happening. But then there are also other applications like those in diagnosis, in the clearance of protein aggregates, or the repair of misfolded proteins. For all of these applications, one of these three instruments can be used. They all offer the same benefits of a low sample consumption, ease of use, in-solution measurements, and being completely maintenance-free. The data I've shown you has been measured with the monolith NT115. We also have the NT-automated, which offers a higher flexibility by combining more than one detection channel. And then there's also our newest blossom, the Dianthus, which measures directly in micro well plates and therefore offers a higher throughput and is the instrument of choice for higher throughput screening projects. I hope you found this webinar interesting and you learned maybe something new or got curious on learning more about how our solutions can maybe help your research. And I would be very happy if some of you soon join our growing community of scientists that use our instruments for their studies in the field of neurodegenerative diseases. If you have any questions, please feel free to contact me via my email, and I'm happy to get back to you. Thank you.
Thanks, Andreas, for this insightful presentation. I already have a question for you. In one of your slides, you briefly mentioned this unusual high cooperativity of zinc binding to tau. Do you have any explanation how this is possible?
Thank you, Aiga, for this excellent question. Let me go back to the slide that you're talking about. So we probably all know Hill cooperativity from the classic textbook example of hemoglobin binding to oxygen. I think there the Hill coefficient is about 2.8. So this 11 that we get for zinc and tau is a totally different order of magnitude. And this cannot be explained by classic cooperativity. And also we, at this point, should only have one zinc ion binding to one tau protein. So this data needs to be explained by a different model. And at NanoTemper, we are actually quite familiar with these kind of plots where we have a linear concentration scale at the bottom and still observe a sigmoidal transition. And this is from our Prometheus instruments. Prometheus is an instrument to measure protein stability. And we have one application called chemical unfolding, where we also have a dilution series of chemical denaturant that is plotted in a linear way. And we observe a sigmoidal transition from a protein in its folded state to its unfolded state. So what we're seeing here for tau is something very similar. Tau is an intrinsically disordered protein. So tau is in the beginning unfolded, and after zinc binding, it partly folds into a partly folded conformation. Or in other words, zinc depletion leads to a cooperative unfolding of tau protein. And this is something really amazing because this apparently high Hill coefficient could not be achieved by any other globular protein. So only an intrinsically disordered protein can do this magic here and can react so sensitively to a slight concentration change.
Ah, I see. Very interesting. Can you maybe also tell our listeners how you would design an MST assay to find aggregation inhibitors? And what are the biggest challenges when measuring fibrils in MST?
Regarding your first question, I have here another slide at the back that might be able to answer this. In MST, we can also perform experiments where we have a labeled monomer and we observe how this labeled monomer gets attached and aggregated by an already preformed fibril. So how you would do this is you would have a dilution series of fibrils, and you could see exactly at what concentrations of fibrils this labeled monomer gets attached. and kind of recruited by the aggregates, because this also has a different MST response than the labeled monomer. This process is also called monomer seeding. And then you have immediately an assay to screen for aggregation inhibitors, because what you can do is you can prepare different preparations of fibrils and then mix them with the aggregation inhibitor, and then just check if your labeled monomers still can be aggregated or if they remain free in solution, and then they don't have the signal change here. And this also brings me to your second question. I think one of the biggest obstacles in measuring these fibrils is that they are not thermodynamically stable at very low concentrations. And that can be a problem because in MST usually you use a very low concentration of labeled molecule, only a few nanomolars. This might be too low for most fibrils to be stable. So the solution is that you keep a higher concentration of fibrils and then you mix them with a low concentration of labeled monomer to generate labeled fibrils, and then you can test them how you would normally do that.
Thank you very much, Andreas.